All right, start our review here for test 3. Looking at our first examples here out of module 10, talking about composite functions. It says find the following and state the domain. Write your answers as a single fraction, without fractions, within fractions. All right, so the first composite function we're looking at is f composed with g. F open circle g. So we're looking at the composition of functions. So we're talking about substituting one function into another. So with f circle g, we want to look at plugging g into f. So let's go ahead and look at the algebra behind that. So we're going to evaluate f with the g of x function. So before we begin, let's state what our two functions are that we're working with. Now f of x, as you can see here in problem 1, is the quadratic function x squared plus 1, and g of x is the square root function 1 minus x. Now before we begin, I want you to talk about any domain restrictions on either of these functions. So we're looking at domain of f. There's no undefined values in a quadratic. Polynomial has a domain of all real numbers. Now g of x, this even root function, we know with domain restrictions, we know 1 minus x must be greater than or equal to 0, right? We cannot have a negative number inside of a square root. So let's go ahead and work on finding our domain restrictions for this even root function g of x. So we'll go ahead and subtract the 1 over. We were solving for x. And with an inequality, when we're working our problem, right, we multiply or divide by a negative, we flip the inequality symbol. So as I'm solving for x, right, we can multiply or divide both sides by -1 in order to get x. And with that said, we are going to reverse this inequality symbol. So that will give us x less than equal to 1. All right. So in order to satisfy the g function, x must be less than equal to 1. So that's what we call a domain restriction on the input function. All right, so that's important. When we're looking at domain of composite function, right, we've got to talk about the input function's domain and, of course, the output function, its domain. We're going to look at the intersection of those two as far as domain of the composite function goes. Now let's go ahead and work on finding the composite function, and we'll see in the end if it produces any domain restrictions. But again, g of x is our input function. So we're looking at evaluating f with an input of g of x, which is the function, the square root of 1 minus x. So let's begin showing our substitution. So wherever we see an x term in the f function, we're going to substitute g of x. So if f of x is x squared plus 1, right, out goes x, in comes the square root of x, 1 minus x. All right, so again, you can see me substituting that g function into f. So that's squared plus 1. So there's the f of x function, right, plugged in, or the g of x function plugged in f of x. So we plugged it in, and our input variable was only one x term in the f function. So out it went, and in came g of x. All right, so let's go ahead and simplify now. Now, as we square a square root, we end up eliminating the square root. So with square root of 1 minus x squared, we get 1 minus x. And we got a plus 1, and we combine our like terms. We got negative x plus 2 for our composite function. So as we do our composition, right, as we find the composite function, f of g of x, we end up coming up with a linear function. So there's f circle g of x, right, negative x plus 2. Now our domain, well, there's no restrictions on a linear function. So our domain would be only the input function's restriction. So again, with x being less than equal to 1, our domain would be equal to what? Negative infinity to 1 with a bracket. So we put it in interval notation. So again, that's our domain of the function. All right, those are all the x values that satisfy this composition function. So again, remember, with domain of a composition function, we got to look at the domain of the input function and the domain of the result and combine those two together. All right, let's see what happens in our next example. Do an R composed with F. So R circle F, or W I should say, R composed with W. So take the R function and the W function. So we're looking at finding R of W of X. Now let's go ahead and mention what R and W are. I'm going to write them over here on the side. So R of X is equal to X minus 3 divided by X plus 7. And Wx, right? Wx is this linear function for X plus 3, which again is my input function, right? So we're going to plug in. Now with this said, there's no domain restrictions on this input function. Right? All real numbers is our domain for a linear function. So as we work on the composition, we're looking at R of 4x plus 3. So where we see X term in the R function, out it goes, and in comes 4x plus 3, our W function. So I'm going to put in parentheses, and we'll go ahead and plug in 4x plus 3 here in the X term or the numerator of the R function. So now we got W of X minus 3, right, as we've taken out X and plugged in W of X in the numerator, all divided by, and as we go to the denominator, so we see our X term, out goes X, in comes that input of W of X, which is 4x plus 3. So you can see us substituting that function, W of X, into the other function, R of X. And our denominator reads plus 7. And as we simplify, of course, the numerators, we combine the like terms. We've got a, 4x plus 3 minus 3. So the 3's cancel out. And denominator, we've got 4x plus 3 plus 7, which is 10. So we add the constant. So we have 4x divided by 4x plus 10. As we simplify down, right, this function here, R of W of X, right? So there's our simplified function. All right, there's our composite function, R composed with W. Now, with that said, our domain, we do have a domain restriction on the result. Got a rational function, right? We cannot divide by 0. So let's go ahead and make note of 4x plus 10 cannot equal 0. So as we solve for x, right, so we subtract the 10 over, we get 4x not equal to negative 10, and we divide out our 4 on both sides. X cannot be equal to negative 10 fourths, or as we reduce, divide out the 2 is a common factor, negative 5 halves. So our domain, right, x cannot equal negative 5 halves. So that would be an interval notation, x less than negative 5 halves. And we need a parentheses on that. Or x can be greater than negative 5 halves. Right, so x less than negative 5 halves, right, or x greater than negative 5. It just can't equal. So again, you can see me writing our domain out. But here's our domain, right, of this composite function, which ended up being a rational function. So we had our x term and down the denominator after we plugged W of X into R as our new composition function. So let's do one more. So example C wants to find R composed with H of X. So again, it's equal to R of H of X. Now what is R and H? Now R of X, again, is our rational function x minus 3 over x plus 7. And H of X, as you can see, is 5 over x. So two rational functions to work with. Now before we begin, we know there's some restrictions on x. We know in H of X, x cannot equal 0. And with x plus 7, we know x plus 7 cannot equal 0. Which means what? X cannot equal negative 7. So there's another domain restriction. So keep that in mind. These are some domain restrictions on my input function. All right, well, let's see what happens with the composite function. So r of h of x, so that's equal to r of 5 over x. All right, that's substituting h of x right into here, what it equals. Now as we do the work, r of x, well, r of h of x, well, wherever we see x term in the r function, there's two of them. One in the numerator, we got x minus 3, so we're going to take out x. We're going to plug in 5 over x in place of it, right, as we substitute this h function in here. So I'm going to go ahead and show that. So there's 5 over x, plug it into the x term, minus 3. All divided by, and denominator reads x plus 7 in the r of x function. Well, again, we're going to take out, right, x, and we're going to plug in that input function of 5 over x. All right, so let's go ahead and plug that in. And then we're adding 7 to that. And now we got to simplify. So if you look at it, we've got fractions within a fraction, which we can't leave. So what I want to do to simplify things, and we'll make a note over here on the side. Let's go clear the fractions. And we'll do that by identifying our least common denominator, which is x. So let's go ahead and multiply numerator and denominator by x, right? We want to clear the fractions. So again, right now we have 5 over x minus 3, all divided by 5 over x plus 7. And as we multiply by the LCD, right, it's x here. Let's go ahead and do that. We got to distribute it through. And we'll go ahead and multiply numerator and denominator by x, and there's two terms. Numerator, denominator, so as we multiply those, you can see we do cancel out that fraction, which is our goal, to clear it out, because we can't leave fractions within a fraction. So numerator now reads 5 minus 3x divided by, as the x is divided out here, we're left with 5 plus 7x. And now it looks better, right? We've cleared out the fraction. We don't have a fraction sitting in another fraction. So we can stop there, but there's our composite function, right? So that's equal to r composed with h of x. Now domain restrictions. As we're looking at our new function, right, we're looking at a denominator, right? 5 plus 7x. We know that cannot be 0. So go ahead to the side here and we'll find out its domain restriction. So let's take that denominator. And as we solve that for x, subtract the 5 on both sides, we get 7x equal to negative 5. Divide out our 7. X cannot equal negative 5 sevenths. If we were to plug negative 5 sevenths into the denominator, it would become 0. So there's a domain restriction, right? So that means we know our domain is all real numbers, x, except for negative 5 sevenths. So x can be less than negative 5 sevenths, parentheses, not a bracket, we don't want it, or it can be greater than negative 5 sevenths. So there's our domain of our function, right? X less than negative 5 sevenths, writing in words, or again, x greater than negative 5 sevenths. So that's composition function, right? Plugging one function to the other. Now let's go ahead and do problem number 2 here, which is the same thing, except now we're going to do composition, in which they give us a particular domain value, right? They give us an input to plug into x, which makes things a little simpler as you simplify these composition functions. So in other words, f composed with g evaluated negative 3 is the same thing as saying f of g of negative 3, right? F of g of x is f of g of x. So we're going to find f of g of negative 3. So we're going to find g of negative 3. So let's go ahead and do that. What is g of negative 3? So I'm going to go over here to the side. All right, I'm going to write down what g of x was given to be. And it's the square root of 1 minus x. So that implies g of negative 3, right, is equal to the square root of 1 minus negative 3, which is equal to the square root of 1 plus 3, which is the square root of 4, or 2. So there's what we're going to be plugging in here. So this is equal to f of 2. So we simplified g of negative 3. And then what's f of 2 going to equal? Well, we know that f of x is equal to x squared plus 1. So that implies f of 2 is going to equal 2 squared plus 1, which is 4 plus 1, or 5. So in the end, as we've done our composition with this input, right, f composed with g of negative 3, it's equal to 5. Right? So again, that's f composed with g, evaluated at negative 3. All right, let's go to the next one. Do the same thing. So you can see these simplify nicely. So moving on, draw a line here, we'll separate our work. But v composed with w, evaluated x equal negative 1, is equal to v of w of negative 1. All right, so let's go find w of negative 1. So we know w of x was given to be the linear function 4x plus 3. So w of negative 1 would be 4 times negative 1 plus 3, which is negative 4 plus 3, or negative 1. So again, we'll plug that in. So this is equal to v of negative 1. And what's that equal? Well, what's v of x? Write it right here beneath it. V of x was given to be this rational function, 4 over x squared minus 9, which implies v of negative 1 is equal to 4 over negative 1 squared minus 9. As we take out x, plug in negative 1. Negative 1 squared is 1. 1 minus 9 is negative 8. 4 divided by negative 8 reduces to negative 1/2, right? So then we get negative 1/2 here. So v of negative 1 equals negative 1/2. And there's our composite function. So there's v composed with w at a input of x equal to negative 1. All right. And our last one, let's go ahead and do this next example, example C. Should be D. But w composed with f of 3. Well, that's equal to w of f of 3. So I'm going to go ahead and work on the input function. What is f of x? And then we'll plug 3 into x to find f of 3. Well, f of x was given to be the quadratic function, x squared plus 1. So f of 3 is equal to 3 squared plus 1, which is 9 plus 1, or 10. So we found f of 3. So that's equal to w of 10. And again, with w of x, well, w of x was our linear function, 4x plus 3. So w of 10 is 4 times 10 plus 3, which is equal to 40 plus 3, or 43. So in the end, we get 43 for our composite function, w composed with f, at an input of x equal to 3. All right, so that's composition of functions, substituting one function into another. Now we'll look at a little bit decomposition, right? We'll take one function and break it up into two. Where composition, you're taking two and putting them together to make one. Decomposition will go the other way. We'll take a break, and we'll continue in a little bit.